Well, hello, and thank you for making the wise decision to learn today. We are going to start by looking at the even numbers from page 175, at least allowing yourself to check. Anytime I'm taking these videos by myself, I feel like I need to do something jazzier with my hands. In fact, I'll play you in paper, scissors, rock. Well, some people call it rock, paper, scissors. That's a huge debate. I don't know. My elementary school did paper, scissors, rock. Show me what you got. That is not normal, by the way. So if that's you, maybe you went to RUSA as well. I went to RUSA. I don't know, but I did know it was weird until I was in college. Anyway, I'm going to play you. Are you ready? Paper, scissors, rock. Show me what you got. Did you win? Did you win or did I win? You'll have to let me know later. Alright, so for our even numbers, you've got your 22 is 30 and 60 degrees. Your 24 is 12 and 60 degrees. Remember, if you have questions on any of the problems from today, odds or evens, that you are welcome to message those on today's post. And if you say that you have a question on 22, I'm just going to work it out and I'll send it to you. Make sure that you have worked out, attempted all of these problems before you're calling it and saying that you don't know how to do it. Especially, I'm actually going to explain this one, but especially when we get to proofs, it is super important that you are attempting them on your own. For this proof in particular, it is very straightforward, so if you tried this whole thing and you're missing a step, or you have the wrong reason down for something, that's a lot easier to fix than if you didn't try at all. If you didn't try at all, then there's not really a starting point that we can start to understand things better. It's just a blank slate. It's like when a student, instead of asking a question, just says, I don't get it. It's hard for us to have a starting place when you just don't get it. We need more of a specific question. So for 26, it tells us angle ABC is a right triangle with a right angle C, and they gave you a little picture if we weren't sure what that meant, and we're trying to prove that A and B are complementary. Hopefully this was easy to prove to ourselves before we start our official proof that if 90 degrees is already taken in this triangle, we've got 90 degrees left over. A and B definitely have to be complementary. So just from our given, we've got a couple of things that we can say. So we've got our given. But then from that, if I know that I'm dealing with a right angle C, eventually I need to talk numbers here. If I'm going to say that they're complementary, I need to show that angle A plus angle B equals 90. So I am going to go ahead and say that angle C would have to equal 90 degrees. And that's just the definition of a right angle. If they tell me it's a right angle, I know it's 90 degrees because it's a right angle. I also need some equation that I'm substituting this into. So because I'm dealing with a triangle ABC, that means I can say that angle A plus angle B plus angle C, I miswrote that the first time, that's an angle C, equals 180 by the Triangle Sum Theorem, our new theorem from yesterday. And then, because I have that equation to substitute it into, I can replace my angle C with 90 by substitution. And now I'm really close because I just needed to show A plus B equaled 90, so now I can subtract 90 from both sides by subtraction, property of equality. And then my last step is saying what I was trying to prove, that angle A and angle B are complementary by the definition of complementary. If they have a sum of 90, they have to be complementary. Okay. So now on to what we are doing today. We've got 4.5 isosceles and equilateral triangles. The goal of this video, of course, give you examples and all sorts of other things, but I'm going to go through things fairly quickly to make the video short. It'll be easier to stream that way because I am going to upload it to YouTube. If you need to pause it or rewind it, that's the beauty of a video. So pause it, rewind it as you need to. Okay, so we're going to start with isosceles triangles, and we actually have names for the parts in an isosceles triangle. So we know in our isosceles triangle that we should have two sides that are congruent to each other. Those two sides that are congruent are called legs. So these guys right here are called legs. the side that is not congruent to the other two, doesn't necessarily have to be the bottom, it's just the part that is not congruent to the other two, is called the base. And then the angles that are next to the base, let's see if I can make my arrow go a little bit further. These are my base angles. The angle that's in between the legs is called the vertex angle, or just the vertex. Okay, so this is all based on which parts are congruent, not necessarily how this triangle is oriented. If I have my isosceles triangle is oriented this way, now I've got my congruent parts are the legs. This side on the left would be the base, the part that's not congruent. These guys would be my base angles, so the parts that are connected to the base or uses a base as one of the sides. And then my vertex is here at the top. Well, not at the top, at the right. So depends on the sides that are congruent, not necessarily how it's oriented. But the special part about an isosceles triangle, not only does it have sides that are congruent to each other, but because they have sides that are congruent to each other, we have a theorem that we can find out things about the angles. So we've got the base angles theorem. This is one that we want to know by name. So far in this chapter of basics of triangles, we've got our triangle sum theorem and then the base angles theorem that we want to know by name. And the base angles theorem says that if we have this situation, I'll give you a triangle ABC. So if I have two sides congruent, if I have an isosceles triangle, then the base angles will be congruent. So in this case, if this is true, then angle B will be congruent to angle C. Oh, I lost my train of thought. I was going to add something there. Sorry. The base angles, if we're having trouble telling which ones are the base angles, they're always going to be across from the legs as well. So they are the angles that are attached to the base, or use a base as a side of the angle, one of the rays. But they are also across from the legs that are congruent. So if I'm wondering which part are the base angles, I'm dealing with B and C. If my triangle is oriented differently, then I will have different base angles. And the converse is true as well. This is one that if I'm using the converse, then I will actually call it the converse of the base angles theorem. So if the conditional said if the sides are congruent, then the base angles are congruent, the converse would say if I have angles congruent, so maybe angle D is congruent to angle E, give it a picture here. So if I have that going on, my angle D is congruent to angle E, then I know that the sides opposite the angles will be congruent as well. So then I know DF is congruent to EF. So put that on the picture, then we know this. So both directions, if I know two sides are congruent, then the opposite angles will be congruent, or the base angles. If I know the base angles are congruent to each other, D and E, or just any two angles in a triangle, then I know the opposite sides are congruent. So this will help us, any figure that I have that involves an isosceles triangle, maybe it's just an isosceles triangle, maybe it has other triangles involved, but will help me solve for angles, possibly sides as well, but usually we're talking about angles. So in our first example, sometimes they will tell you it's an isosceles triangle, but a lot of times they'll just mark congruent sides, or they'll tell you the lengths of the sides. This is 5, 5, and 7, and so you'll just know those two sides have the same length. So they're congruent. That means that the sides opposite them, or the base angles, have to be congruent as well. So in this case, the sides opposite are my 40 degrees and y. So that helps me to determine that y will equal 40 degrees. No work to show for that one. And then because I'm dealing with a triangle, I can use the Triangle Sum Theorem to find x. That I have x plus 40 equal to 180. And then subtracting my 80 from both sides, x is equal to 100. So anytime I notice an isosceles triangle from now on, I'm looking for, okay, what angles do I know are congruent because it's isosceles. So for example 2, still have an isosceles triangle, so it's similar in that way. The only difference is that I'm given the vertex angle instead of the base angles. But I'm still asking myself what parts will be congruent. My angles that are opposite my congruent sides are x and y. So that means that x and y have to be the same. Even if you want to give it the same variable, you can. But if I figure out how many degrees are between the two, I can divide by 2. So by taking 180, subtracting 20, I get that there's 160 degrees between the two of them, and then I can divide my 160 by 2 to get that both x and y have to equal 80. If you wanted to set up an equation for this, you could make them the same variable. We would need them to be the same variable to solve, but we could say x plus 20 equals 180. So we have a 2x, subtracting the 20 to both sides, I'm still going to end up with 160, and then dividing by 2, I still end up with 8. Just like we talked about yesterday, when you're solving something like this, I know you can do this in your calculator or do it in your head, but I want to see at least this, where you're telling me I subtracted this amount, I divided by 2. It's not a ton of work to show, but it is showing me a little bit what your thought process was. Okay, so example 3, we could have more than one triangle or more than one isosceles triangle in one diagram. Kind of depends on what we're given, whether we need to solve for a particular part first, but again, it helps to mark the angles that I know are congruent. So on my isosceles triangle on the left, I know that the angles opposite my congruent sides will be congruent, and then I know my angles that are opposite my congruent sides here will be congruent. Remember, when we're marking angles or sides congruent, we're not saying with the two arcs here, we're not saying that those angles are larger. We're just pairing these two together and those two together by giving them one mark and these two marks. Okay. So in our triangle on the left, my two congruent pieces lets me know that this angle has to be 50 degrees as well. So now I can solve for x in this triangle by taking x plus 50 equal to 180 using the Triangle Sum Theorem. When I subtract from 100, get that x has to be 80. I'm seeing a pattern, 80. And then for angle y, I don't have one that just tells me what either of those are, but I do have the vertex angle. So this is an instance where I could call this y as well, since they're congruent to each other. And I know my 2y, or y plus 100, have to equal 180. So 2y has to equal 80, and y has to equal 40. It's never a bad idea to go back in and plug in the angles that you found and make sure that any triangles we're dealing with add up to an interior angle sum of 180. If you're wanting to check a whole diagram like this, a quadrilateral should have a sum of 360 on the inside, if you're curious about that. Okay, and then last of our isosceles triangles, This last one, it seems like there's not a whole lot of information here, but anytime we're trying to solve for x, we're just looking for a true equation. And because it's isosceles, we know that the base angles will be congruent by the base angles theorem. These angles that are opposite my congruent sides. So if they're congruent, that means that x plus 44 has to equal 3x. That if we subtract x from both sides, 44 equals 2x, and x equals 22. I'm going to plug that in, find that both of them are 66, looks like. Okay, so that's isosceles triangles. Really just looking for base angles that are congruent to each other. Which brings us to equilateral triangles. So we know that equilateral triangles have all sides congruent. So that means, from what we just learned, I'm going to get some letters so that we can talk about this triangle. From what we just learned, because we have sides that are congruent to each other, that means that we can use the base angles theorem. So by the base angles theorem, if my AB is congruent to BC, that means that the angles opposite AB and opposite BC have to be congruent. But I also know that BC and AC are congruent, so the angles opposite BC and opposite AC have to be congruent. If we went one more, we could look at AC and AB. They would tell us that C and B have to be congruent. So by using the base angles theorem 3 times, we see that not only is it an equilateral triangle, but all equilateral triangles, so we'll say equilateral, lost myself, yeah. Equilateral triangle, if and only if, I didn't really use a whole sentence there, did I? It is an equilateral triangle, if and only if it is an equiangular triangle. So that's our word for saying that all of the angles in a polynomial are the same. So we can have other shapes that are equiangular. You could have a pentagon that's equiangular. It just means all 5 angles are the same. Any polygon we can have equilateral or equiangular. And it just so happens that for a triangle, if it's one, it's the other. And this is a biconditional statement, so if we had all 3 angles that were congruent to each other, we would automatically say, oh, this has to be equilateral. All the sides have to be the same. Because they're all the same, that means that we automatically know the measure of each angle. So if I have 3 angles and they're all the same, and we know they have to add to be 180, that means that 3x equals 180. And each of those angles has to be 60 degrees. So not only does the equilateral triangle tell us that we've got all angles congruent, but we actually automatically know what each of those angles equal. It's going to be 60 degrees no matter what. So if I'm given something like this, for example 5, I'm noticing I have all sides congruent, so sometimes they mark them, sometimes they'll give us a measure. Don't be thrown off by the measure. If they're not asking us to find a side, we don't have to worry about it. But because this is an equilateral triangle, all sides the same, then I automatically know all my angles are the same. It's kind of hard to draw. And because all my angles are the same, that means that they each equal 60 degrees. So I would need to know, it almost seems like we don't have enough information, but I would need to know that since it is equilateral, that means that 2x minus 8 has to be 60 degrees. And then I can solve from there. There are fewer questions that they'll ask us with equilateral triangles. They're more isosceles type questions just because there's not a whole lot of variation. You can't really solve for the angles in an equilateral triangle because they're always going to be 60 but they might give us something like that, or they might give us a problem that involves both. So we're going to end here. And go ahead and draw your diagram. We're looking for the measure of angle DEF. And we're noticing right off the bat that we've got isosceles triangle here on the left. A triangle EFG is an isosceles triangle. By the way, I don't think I mentioned yesterday, but we can name triangles with any order of the three vertices. So I can say triangle EGF, triangle FGE, triangle FEG. It doesn't matter the order because no matter what, it's one direction. There are only three vertices. And then I'm noticing that my triangle DEG is equilateral. So anytime I see an equilateral triangle, I'm saying, I know that my angles for my equilateral triangle are all 60. For my isosceles triangle, I know that the base angles have to be congruent, so opposite of my congruent sides are congruent angles, so that has to be 30. And then this part's not even asked for, but if I did want to find that, then I would just be taking my 180 and subtracting 60 from it. So this would be my 120, and this is surely not drawn to scale. My bad. That's what happens when you make up your own problems. Sometimes they turn out great, but sometimes they don't. So then, yeah, this is really going to not be to scale because the question asked us to find the measure of angle DEF. So here's my DEF. So the measure of angle DEF ends up being 90 degrees. Yeah, that doesn't look like 90 degrees. Well, listen, people, it's icy outside. It'll be okay. Okay, and that's all we have. So your homework is going to consist of basically different problems involving isosceles equilateral triangles. What I like about this point and where we're at is that we're just building up different things that we can use in a diagram where eventually we could have a really complicated diagram and we know our vertical angles are congruent, we know alternate interior, alternate exterior corresponding are congruent, same side interior supplementary, we know that triangles have a sum of 180 degrees, we know that opposite angles in a isosceles triangle are congruent, we know equilateral triangles have 60-degree angles, so we're adding a lot to our angle repertoire. Linear angle pairs add up to 180. Wouldn't want to leave them out. Okay, so that is it. We'll end this out with one more paper, scissors, rock. I don't know if you won that first game or not, but this is your time to either redeem yourself or for me to just take the gold. We got paper, scissors, rock. Show me what you got. Did you expect me to do the same thing both times? I didn't even expect me to do inspect? Suspect. Oh, guys, I need to be around people. All right, enjoy the rest of your weekend, unless, of course, you are watching this on Monday, and in that case, I will see you tomorrow. You have waited until the last minute. Goodbye.